So let us see what is the basic difference between root locus plot and Bode plot. So nobody is going to ask you this question, but uh, at the initial stage, you should understand exactly what we are doing different in case of Bode plot. So I have given you a very simple example, that is in root locus plot. What we are doing is GSHS is given, and k into s plus 4, s plus 3, s plus 7, all these things are given. We are supposed to find out the root locus plot for variable gain of k. Now what is k? So this k factor you will not find in Bode plot. K factor is found in root locus. So this is a question which will not be asked in the exam, but to understand the difference between root locus and Bode plot, first you have to understand. So this k value in case of root locus, we can set the way we want. So this is the external gain k. And with respect to the external gain, we are trying to find out first the characteristic equation. And after finding the characteristic equation, we are finding what are the poles, that means position of S. And then we are finding for which gain the system is going to be unstable, for which gain the system is going to be stable, and all other things. Uh, so that is actually what is given as root locus. So k is an external gain in case of root locus. And biggest thing is k is not a function of frequency. That is a very important thing we have to understand. In case of root locus, k is not a function of frequency. So k is a separate kind of a factor. We can change the value of k from 0 to infinity by changing the external components like resistor, capacitor, and inductor maybe, which are the gain quantities, gain controlling quantities. So k is something we can control externally, and k is not frequency dependent. Very important thing. That is the case of root locus. So k is a gain not directly determined by frequency. That means k is not frequency determined. There is no s term in k. K is a separate gain. So in a system, we decide how much gain of k we want. We put that, and then we find out whether the system is stable or unstable depending on the pole position. That is root locus. What is Bode plot gain? So we have discussed 3 hours. We have not solved that way a very perfect numerical, complete numerical we have not solved. Still we are in the initial stages. This hour also will go in the initial discussion. We are still building up for Bode plot. So in Bode plot, what given is GSHS equal to s by s plus 4 divided by s plus 3 and s plus 7. The same transfer function I had given at the top, if you see. Okay, so but only in case of Bode plot, that k factor is not there. What actually we are supposed to find out is two things. One is the amplitude of Bode plot, which is given by mod of g j omega h j omega, and j omega is nothing but what we call it. J omega is the frequency. So s is equal to j omega. That is something we have to substitute. Now if we are substituting h is equal s is equal to j omega, then we can find two things. We can find amplitude. So first we are substituting s is equal to j omega in case of GSHS, and then we have to find how much is the mod value. So this is mod of, instead of s you are substituting j omega, so numerator becomes 4 plus j omega, denominator becomes 3 plus j omega, 7 plus j omega. Now you find out what is its amplitude. So a plus j omega, what is amplitude of that? So it is having two parts. One is amplitude, another is phase. So amplitude with respect to omega from 0 to infinity, phase with respect to omega from 0 to infinity. So this is the difference between root locus and Bode plot. In root locus, we had been changing the value of k from 0 to infinity, and k was a gain which was not determined by frequency. But in case of Bode plot, we are actually changing the input frequency. Generally, input frequency in our lab experiments are given from function generator or signal generator. So the same system we are connecting, and we are just changing the frequency knob. We are giving different input frequencies, and we are checking what is the overall gain GSHS at different values of omega. And I have calculated some of the omegas below if you check. So overall amplitude factor becomes root under of 4 square plus omega square divided by root under of 3 square plus omega square plus root under of 7 square by omega square. Because the transfer function is given as s plus 4, that means 4 plus j omega divided by 3 plus j omega into 7 plus j omega. From there you are finding this refractors. Now depending on different input frequencies, suppose somebody is keeping input frequency as 5 radian per second. Instead of omega, you are supposed to substitute 5. So this is omega square, that means 25. So I have calculated how much will be the gain, system gain for omega is equal to 25. ये सब कुछ तुम लोगों को Bode plot में नहीं करना है, कुछ भी नहीं करना है, but I am just telling you how the Bode plot is developed. So in GSHS, that is G omega, H omega mod of that, always amplitude plot comes in positive. Okay, so that will be a mod of that we are taking. And whenever we are converting this thing into dB, at that time there may be negative. Okay, but this is not dB. Generally, Bode plot is plotted in dB. But here we are finding that it is mod of that, so it will be positive. So in case of omega, if you are substituting 5, you are getting that numerator is root under of 4 square plus omega square, that is 16 plus 25. Denominator is 3 square plus omega square, that is 9 plus 25, because we can supply different input frequencies now to the circuit whose GSHS is given. Now, if you are just calculating it by omega is equal to 5 radian per second, you are finding it as 0.127. That is the gain. That means this system at 5 radian per second frequency input is going to give you a gain of 0.127. If I ask you what is its DC gain, so DC gain means in case of omega substitute 0. In that case, the DC gain will be 4 divided by 3 into 7. That means DC gain will be 4 divided by 21. DC gain means omega is equal to 0. So that is equal to 4 by 21. Omega is equal to 5 radian per second, gain is 0.127. Somebody wants to check omega is equal to 10 radian per second. In case of that, omega square you have to substitute 100, or omega is equal to 10. In that case, you are finding that the system gain reduces to 0.0845. So this is what we are doing in case of Bode plot, and previously whatever I had shown, that is was in case of root locus. So in case of root locus, k is a external gain which we can change at our own will, and in case of Bode plot, we cannot change at our own will. We cannot change the gain, but we can supply different input frequencies, and depending on that, the system gain is going to be changed. So in root locus, the k or the gain was external. That is the first difference. In case of root locus, the k was at our control. We could control or we could change the value of k at our will. But in case of Bode plot, this GSHS is not in our control. GSHS is already given. In our control, frequency is there in our control. So by changing the frequency, we can change the gain of the Bode plot. So biggest difference in case of Bode plot and root locus. In case of Bode plot, the gain is not frequency dependent. But in case of root locus, I'm sorry, very much sorry. In case of root locus, the gain is not frequency dependent. But in case of Bode plot, the gain is very much frequency dependent. You find here the same system at 5 radian per second, it is giving you gain of 0.127. Same system, GSHS, at 10 radian per second, the gain decreases. And we are plotting this. So we are plotting the phase as well as we are plotting the gain for the Bode plot for varying input frequency. So what are the variable quantities in case of root locus and Bode plot? In case of root locus, the variable quantity is gain. In case of Bode plot, the variable quantity is frequency. So this is something that we have to understand. Next, we are still now in the basics of plotting root locus. Actually, what we do is we plot the gain and we plot the phase for different frequencies. So how to plot the gain? Okay, as I had shown you previously, s plus 4. So in case of gain, it will becoming root under of s square, that is omega square plus 16. Denominator will become root under of 9 plus 16. 9 plus omega square. This s plus 7 will become root under of 49 plus omega square, likewise. Is this gain thing visible? Next page I have uploaded. Angle of GSHS, is it visible? Some student please acknowledge. Is this page visible? New page which I am showing?
Yes, sir.
Okay, so now we are going to find what is the angle. So how to find the angle? So previous page I showed you how to find the gain with respect to frequency. Now I'm going to show how to find the angle. So first thing, you have to substitute s as j omega. As soon as you are substituting s is equal to j omega, that is real plus imaginary, that is 4 plus j omega. What is the angle of that? Tan inverse omega by 4. Because we know how to find the angle tan inverse imaginary by real. So first step, substitute s is equal to j omega. Here I am showing, okay, g j omega, h j omega. So substitute s is equal to j omega, j is the imaginary. Find what is angle. So this is tan inverse omega by 4. Denominator, it will be tan inverse omega by 3 and tan inverse omega by 7. And whenever the angles are there, they will get added. Okay, and whenever numerator and denominator are processed, denominator angles are subtracted from the numerator angle. So what is the overall angle of this system, which is given by GSHS s by 4, s plus 3, s plus 7? So for s plus 4, it is tan inverse omega by 4. For s plus 3 at the denominator, it is minus tan inverse omega by 3. And for s plus 7 at the denominator, it is minus tan inverse omega by 7. Now I have shown you two cases, that is find the gain for omega is equal to 5 radian per second and omega is equal to 10 radian per second. And in that case, you had found that the gain was 0.127 and 0.08. That means omega is equal to 5 radian per second. It was around 0.127 or something. Previous page we have seen. And for omega 10 radian per second, the gain was 0.08 or something. That means the gain was changing with respect to frequency. That is what I'm trying to point out. Whether it is increasing or decreasing, it doesn't matter, but gain was actually changing with respect to frequency. In this case, you will be finding that the phase angle also is going to changing. Phase angle means angle between input and output. So that is called as a system phase. So this is tan inverse omega by 4 minus tan inverse omega by 3 minus tan inverse omega by 7. Substitute omega is equal to 5 radian per second, because omega in case of Bode plot, we can change from 0 radian per second up to infinity radian per second. So here if we are substituting omega is equal to 5 in all these three equations, you are going to get angle 51.34, that is for omega by 4, that is 5 by 4, and tan inverse omega by 3, that is 5 by 3, the angle will be minus 58.73, and minus tan inverse omega by 7, it will be minus 35.52. So what angle you are getting at 5 radian per second is minus 43.11 degree. The same system with omega is equal to 10 radian per second is going to give you minus 60.086. So this is something what we want to find out in case of Bode plots. So for different frequencies, you have to plot different phases. Now for given system, there is 1 0 and 2 pole. Now I am giving you a generalized thing. So this is something you must have to understand. Looking at the plot, okay, or looking at the GSHS, you should be able to tell me what is going to be the phase at infinity. So here we will be finding that if you are substituting omega is equal to infinity, the numerator will be 4 plus j omega. Omega tends to infinity, that means tan inverse infinity by 4. Tan inverse infinity by 4 will give you gain as, or sorry, phase as plus 90 degree. Same thing if you are doing below, that is tan inverse omega by 3, omega tends to infinity. Because in case of Bode plot, we have to change the frequency from 0 hertz to infinity hertz. So at 0, numerator phase will be 0, denominator phase also will be 0. So at GSHS at omega is equal to 0, all the phase will be 0. Okay, so in this equation, G, j omega, H, j omega, substitute all the omega is equal to 0. You'll be finding it omega is equal to 0 radian per second, which is called as a DC phase. You'll be finding that phase is equal to 0. But now you have increased the omega up to 5. You are finding phase is minus 43.11. Further, you have increased the omega, that is input frequency, to 10. You can change the input frequency from function generator or signal generator. You are finding the phase is still decreased. So it has gone to minus 60 degree. Now the question is, when omega is infinity, how much this phase is going to be? So you'll be finding that the maximum phase will be minus 90 degree. Why minus 90? So this is something I want to tell you. For every s, the maximum phase at infinity can be 90 degree. Okay, so s plus 4 means 4 plus j omega. That means tan inverse omega by 4. What is going to be the maximum value of omega? Maximum value of omega can be infinity. So tan inverse infinity by 4, that means tan inverse infinity. How much is that? It is pi by 2 on 90 degree. So this numerator tan inverse omega by 4 at omega is equal to infinity, this tan inverse omega by 4 is going to be 90 degree. Minus tan inverse omega by 3, this is going to be minus 90 degree. Minus tan inverse omega by 7, this is going to be minus 90 degree. So what you are finding is every first order pole, they are going to produce 90 degree phase. So in this case, in numerator there is one s, denominator there are 2s. That means what is the overall numerator phase at s is equal to infinity? It is going to be plus 90. So s plus 4 is going to produce a phase of plus 90 at s tends to infinity. S plus 3 will produce a phase of minus 90 because this s plus 3 will go to the numerator. So this s plus 4 plus 90 and s plus 3 minus 90, they will get cancelled. So what will be the net phase? Net phase will be for s plus 4, that means minus 90. That's why when s tends to infinity, you'll be finding that the net phase will be minus 90 degrees. So just looking at the transfer function only, you should be able to tell me that what is going to be the final phase at omega tends to infinity. So there's a very simple trick I told you, and through numerical also you can prove that. So I have given some kind of reasoning for this. That is, for given system there is only 1 0. 1 0 means at omega tends to infinity, that will give you phase of plus 90. And two pole. So every pole, first order pole, if it is a first order pole, it is going to give you phase as plus 90. If it's a second order pole, it will give you phase as plus 180. Sorry, minus 180. If it is a second order 0, it will give you phase as plus 180. So every order is going to give you 90-degree phase. If it's at numerator, that means plus 90. If it's a denominator, it is going to give you minus 90. So finally, I'm telling you, first order 0, that means s plus 4. At omega tends to infinity, phase is plus 90. 1 by s plus 4 or 1 by s plus 3, that means single order pole. It is going to give you at omega tends to infinity, it will give you the phase as minus 90. S square plus 7 or s plus 7 whole square at the numerator, that means this is a second order 0. This will give you phase of plus 180. And suppose 1 by s plus 3 whole square, that means s plus 3 second order pole at the denominator. This will be giving you phase as minus 180. So in this case, there are one first order 0 and there are two first order poles. So one phase of 0 and one phase of pole 90 and minus 90, they cancel each other. That means for one pole at the denominator, you will be finding at omega tends to infinity, the phase is going to be 90 degree. Same thing you can find out by putting an extremely high omega. So if you are putting extremely high omega in this equation, so whatever equation you have, that is tan inverse omega by 4 minus tan inverse omega by 3 minus tan inverse omega by 7. So substitute omega is equal to 10,000 radian per second. You'll be finding that omega by 4 is going to give you 89.97, almost 90. Omega by 3 is going to give you almost 90. So these two cancels each other. So what prevails is omega by 7. So that is going to give you almost minus 90. That means that very high frequency, omega is equal to 10,000 radian per second, very high frequency, the phase of the system is going to be minus 90 degree. So one conclusion has been drawn, or one generalized case has been drawn. Note phase. So how is going to be the phase for infinity? So for every single pole at denominator, maximum phase as omega tends to infinity is minus 90. So for every single ordered pole, double ordered minus 180, triple ordered pole, that will be minus 270. So there's a very simple thing you have to understand. So for every single ordered pole at denominator, maximum phase is minus 90. Maximum phase means when omega tends to infinity. For every single ordered 0 at the numerator, maximum phase omega tends to infinity is plus 90. So from the given GSHS, we very easily can find out that max phase for omega tends to infinity will be plus 90 at the numerator and 2 minus 90 at the denominator. That means that omega tends to infinity, the net phase will be minus 90. So this is something also which I wanted to tell you. Now I'm going to launch a next page. Amruta, are you there? Just Amruta G, you just respond if you're there. Amruta, are you there?
Yes, sir. Yes, sir.
Yeah, so you asked this question, and this question is very much reasonable. Somebody asked why 1 by s line has to have a slope of minus 20 dB per decade. So very simple it is. S, if it is s at the numerator, that means single 0 if at the numerator, the slope will be plus 20 dB per decade. But if it is 1 by s, that means single pole at the, or first order pole at the denominator, it will be having slope as minus 20 dB per decade. What is meant by minus 20 dB? That means in one decade frequency, like 1 to 10 if you are going, or 10 to 100, the amplitude should drop by 20 dB. That means that it will be a downward slope for every decade. Decade frequency means, I told you last day, 0.1 radian per second and 1 radian per second. It is called as a decade. 1 radian per second and 10 radian per second. It is called as a decade. So what is your GSHS now? So Amruta, especially you raised this question, so I'm explaining, but for all, GSHS is equal to 1 by s. 1 by s means 1 by j omega. So what is g omega, h j omega? If you just taking the mod, so this j goes off. So this is just 1 by omega. So at 10 radian per second, so we are finding between 10 and 100, how much is the gain. So as the frequency is increasing, as it is 1 by s, as frequency is increasing, you will be finding that the gain is reducing. because the gain function is 1 by omega. So bigger the omega, lesser will be the gain. So I gave you, again I'll be telling from the first, GSHS for Bode plot, I have given you 1 by S. You have to draw the Bode plot, amplitude plot for 1 by S. And what will be the line? It will be a line 20 dB per decade. Okay, or negative 20 dB per decade, not positive, because this is a pole. Okay, first order pole, it will be minus 20 dB per decade. Second order pole, minus 40 dB per decade. Third order pole, minus 60 dB per decade. Why so? Okay, why should you just take my word and draw like that? Again, if I say there is S, only S, that means GSHS is S, first order pole at the numerator, it will be having plus 20 dB per decade. So zeros are having positive rising kind of slope, and poles are having falling or negative kind of slope. Why is it so? So just plot it for different values of omega. So GSHS is 1 by S, 1 by j omega, or G j omega, H j omega, remove that j because it is root under of 1 by omega square, that means 1 by omega. I think you understand this line, how to find the S is equal to j omega, and after that how to find the amplitude. Now substitute both these values. So omega is equal to 10 and omega is equal to 100. So for omega is equal to 10, the gain will be 1 by 10. For omega is equal to 100, the gain will be 1 by 100. Now here I am going to find out slope. So for omega is equal to 100, I am calling it x2 point. Omega is equal to 10, I am calling it x1 point. And gain is nothing but y2. So y2 is 1 by 100 because it is 1 by omega. And y1 is equal to 1 by 10 because this is this is y1. So what is slope? Slope is y2 minus y1 divided by x2 minus x1. That is 1 by 100 minus 1 by 10. We have to find out how much is 1 by 100 minus 1 by 10. And what is x1 and x2? x1 and x2 are nothing but decade. Same thing you could find for 1 and 10 also. Okay, at 1 radian per second it is 1, and at 10 radian per second it is 1 by 10. So that could have been y1 and y2. But the same thing happens for 10, 100, same thing happens for 100 and 1000 because it's a straight line. The slope at every decade is going to be same, minus 20 dB per decade. Amruta asked how to calculate it. So this is how to calculate it. So for 10 radian per second, the gain is 1 by 10. For 100 radian per second, the gain is 1 by 100. Now you have to convert this thing into dB. Okay, so slope between 10 radian and 100 radian. So y2 you have to write first because 100 is the x2 frequency. So 20 log 1 by 100 minus 20 log 1 by 10. So this is y2 in dB and this is y1 in dB. Okay, so 20 log 1 by 100 minus 20 log 1 by 10. And if you are just doing it, you'll be finding it as 1 by 100 divided by 1 by 10, or this will be 10 by 100. So this 10 goes up and 100 comes down. So 20 log of 0.1, 20 log of 0.1 means minus 20. Somebody wants to do it between 10 and 1. So in that case, it will be 20 log 1 by 10 minus 20 log 1. Again, it will be 20 log of 0.1. 20 log of 0.1 is nothing but minus 20 dB per decade. So this is this slope you have to find. So x2 minus x1, x2 minus x1 is 110. So we know it's a decade. Decade means 10 frequency. So if I give you 5 radian per second, decade frequency of that is 50 radian per second. If I give you 1.5 radian per second and ask you to find slope, so you have to find what is the amplitude at 1.5 radian per second. And you have to tell me what is the gain at 15 radian per second, because 1.5 and 15, 1.5. Okay, so that they are actually decade frequencies. So in this case, we know the decade frequency is 110. So there is no confusion with x2 and x1. And we have to find out what is the gain difference between 100 radian per second, that is 20 log 1 by 100. So this is dB gain, minus gain at 10 radian per second, that is 20 log 1 by 10. So if you do that, it will be log a minus log b is equal to log a by b. 20 is there constant. So log 1 by 100 divided by 1 by 10. So that will be 10 by 100, 0.1. That will be minus of 20 dB per decade. Now somebody wants to find the slope between 10 radian per second and 1 radian per second. Again, the same thing I told you. So it is 20 log 1 by 10 minus 20 log 1. Again, the same thing, 20 log 0.1 minus 20 dB per decade. Somebody can ask, can you prove that 1 by s square line, it has minus 40 dB per decade? So in that case, only the function will change. So for 100, so for 100 radian per second, it will be 20 log 1 by 100 square. Because now what is my GSHS? Now my GSHS is 1 by s square, that is equal to 1 by omega square. Okay, so 1 by j square s square. J square again will be giving you a minus 1, but whenever you are taking mod of amplitude, it will be 1 by omega square. So at 100 radian per second, it will be 1 by 100 square minus 20 log 1 by 10 square. That means it will be 10 square by 100 square. That means it will be 20 log 0.01. 20 log 0.01 is nothing but minus 2. So in that case, you are going to get is minus 40 dB per decade. Similarly, if it is 1 by s cube, it will be minus 60 dB per decade. That means for every 1 by s, you have to uh, decrease the slope by minus 20 dB. So for 1 by s, the slope is minus 20 dB per decade. For 1 by s square, the slope is minus 40 dB per decade. For 1 by s cube, the slope is minus 60 dB per decade. Samely for 0, first order 0, s, the slope is plus 20 dB per decade. For s square, the line has plus 40 dB per decade slope. How? So s square means omega square. S square means j omega square. So remove j. So s square means omega square. So what will be the slope? 20 log 100 square minus 20 log 10 square. That means this will be 20 log 100 into 100 by 10 into 10. That means 20 log 100. So 100 log 100 means 2. Okay, so that will be 20 log 100 square minus 20 log 10 square. That means 20 into 2. That is going to be 40 dB per decade. So for S, it will be 20 dB per decade. S means a single 0. S square means it's a squared 0. S cube means it's a 3 0. So for every S, so for every order, you have to keep on adding 20 dB per decade in your overall line. Okay, so all these lines I will now show you together. I guess all these things are visible to you now. Okay, I'm going to launch one thing. Is this line visible? Similar graph paper. Can anybody confirm?
Yes, sir.
Okay, so now I have drawn all the lines. Okay, so this is a similar graph paper. I have drawn it today itself. So I'm starting from point 1. Somebody wants to start at 0.01, no problem. He can do that. So I have taken the first point, x-axis. X-axis is log of omega. Be very careful whenever you are drawing similar graph paper. X-axis you write log of omega. Okay, so this is log of distance. This distance is log of 0.1 minus log of 0.2. So here we will write 0.2, but actually this point is log of 0.2. This point is log of 0.3. This point is log of 0.4. This point is log of 1. Okay, that means it is going to be 0. And here log of 0.1, that means this is going to be minus 1. Log of 10, that means it is going to be 1. Okay, so this is how the lines are drawn. So you can take a screenshot or I will be posting you all these things today itself. Yesterday night also I have posted 2 of our previous or 3-hour session that I posted. That is one very basic of Bode plot that we had discussed on Monday, and 2-hour session that we had discussed on Tuesday. Okay, so yesterday's lecture is yet to be taken, so I will do that and I will upload today itself. There we will be solving numerical. So are these 7 lines understood? So first line, that is line 0. Line 0 is nothing but the baseline. So this is 0 dB, you can check. Okay, then I have taken this much. So this is 20 dB minus 20 dB, 40 dB minus 40 dB, and 60 dB minus 60 dB. So what is this point minus 60 dB? So this point is called as 0.1 minus 60. What is this point? This is called as 0.1 minus 40. This point is called as 0.1 minus 20. So you should be having good knowledge of coordinate geometry also, and you should be able to plot the points. Now this point is 0, 0. This point is called as origin. That means amplitude is also 0 and frequency is also 0. Very important thing, again I'm repeating for the last time, x-axis is log of omega. Unit you can write down radian per second. So it is 0, 0 means amplitude here, this point is 0 dB, and frequency is log of 0. Okay, so we are calling that as 0 only. So this is called as origin. Now this higher point is 0.120. So I have made a mistake actually. This also should be 0.1 comma 0. So this point x-axis is 0.1. So this first 0 is actually wrong. This should be 0.1 comma 0. So this upper point is 0.1 comma 20. Then it is 0.1 comma 40, and it is 0.1 comma 60. Now this below line, okay, which is going fast with a slope of 60 dB per decade. Why this is 60 dB per decade? Because it is starting at 0.1 comma minus 60. Okay, that means 0.1 comma minus 60, and after 1 decade, so 0.1 ka decade I 1. Okay, 1 ka decade I 10, 10 ka decade I 100. So between 0.1, that means 0.1 to 1, in this, it has achieved a slope of 60 dB, you can find out. So this is 20 dB, this is 40 dB, and this is 60 dB. So you can see here also this is minus 60, minus 40, minus 20. That means every unit you are dropping by 20 dB. So you are finding that this line, below line, okay, which is I'm calling as line 1, either you take from 0.1 to 1 or you can take from 1 to 10. Okay, so if you're taking 1 to 10, then also it's a decade. Point 1 to 1, then also it's a decade. So it's a straight line, so slope is unchanged. Line 1, what are the points you have to connect, and you have to extend. Okay, so this line doesn't stop here, all the lines have stopped here. It extends in both the sides, in the right side also it extends, left side also it extends, like this. So I have just shown you a part of it, that is point 1 to 10. 2 decades I have shown you. So in 1 decade it rises by 60 dB, because this is S cube line. So whenever I'm saying S cube line, that means it is triple slope. So for every S, it is rising by 20 dB per decade. So for S cube, it will be rising by 60 dB per decade. So you can find here it is minus 60, and here it is 0 dB. So how much is the difference in y-axis? It is 60 dB. And how much is the difference in x-axis? It is 1 decade. Okay, so that's why this line, line 1, which is called as, which is passing between point 1 minus 60, that is this point, and all these lines, all this 1 by s square, 1 by s square, s cube, 1 by s cube, all these lines will be passing through 1 comma 0. These are protocols. So every numerical, the same thing you have to do. So these are the slopes you can draw, because line 1 is a slope of plus 60 dB per decade. Line 2 is a slope for plus 40 dB per decade. Line 3 is a slope for plus 20 dB per decade. Line 4 is a slope for minus 20 dB per decade, because this is 1 by s. Okay, this is a pole, first order pole, 1 by s. So you can check what is line 4. So line 4 is a slope of minus 20 dB per decade. Why? Because it is starting from point 1 comma 20, and in 1 decade, that means point 1 to 1, in 1 decade it should fall by 20 dB. So at point 1 it is amplitude is 20 dB per decade, and at 1 it is at 0 dB, and then difference is 20 dB minus 0 dB is 20 dB. So in 1 decade it is falling by 20 dB. So what is the slope of line 4? It is minus 20 dB per decade. If you check line 5, okay, that is starting from point 1 comma 40, and it is coming to minus 40 at 10. Okay, so that means it is starting at point 1 comma 40, and in 1 decade frequency it has fall by 40 dB, and it has come to 1 comma 0. So y2 minus y1, that is 0 minus 40, that is minus 40, and decade, it is decade, that is 0.1 to 1. So in 1 decade it has fallen by 0 minus 40. Always you have to do y2 minus y1, or you can do here, that is minus 40 minus 0 in 1 decade. Okay, so always the next minus previous. So minus 40 minus 0, that is minus 40, and divided by 1 decade. So what is the decade frequency here? 1 to 10. So that's why this line, line 5, it is called as 1 by s square. So how to draw all these lines I have shown you, and this is very easy actually. There is no rocket science. Only thing is, x-axis is not linear, x-axis is logarithmic. That's why it's called as a semi-log graph paper. So one axis is logarithmic, another axis is linear. So y-axis is linear because you can find distance between minus 20, again another minus plus 20. So every 20 dB is having the same distance. So that's why it is called as a simple or linear kind of characteristic in the y direction. Okay, so after all these basics of how to draw the plots for s square, 1 by s and 1 by s square and all, so all the basics related to amplitude Bode plot for single type of poles, they are done. So let us go take some more basics related to Bode plot. So I told you that in Bode plot we have to mainly plot two plots, that is magnitude plot or log of V naught by V in, or rather 20 log V naught by V in. And next is phase angle of phi, okay, or phase plot we have to plot. So in the first plot, that is in the magnitude plot of open loop transfer function GSHS, it is plotted with respect to omega in from 0.1 up to a higher frequency. And in graph 2 phase angle, we plot phi with frequencies 0.1 to higher frequencies. So in magnitude graph, we convert all the ratios, magnitude ratios into dB. So formula is 20 log gg omega h omega. That is what we do. Decade frequencies f2 as to f1. This is 10 as to 1. So if we take 10 kilohertz, 100 kilohertz will be its dB frequency. If we take 1.2 kilohertz, then 12 kilohertz will be its dB frequency. Now g h j omega, it is also called like that, is equal to V output by V in is equal to 0.1. In that case, GSHS is 20 log 0.1, that is equal to minus 20 dB. So for some case, if suppose at certain frequency, gh of j omega becomes zero point 0.1. So how to convert that thing into log is 20 log of gh at that frequency. So 20 log of zero point 0.1 is minus 20. Now here we have seen zero point 0.1 goes to minus 20 dB, 0.01 goes to minus 40 dB, and 1000. So anything less than 1 actually will give us negative value. Anything greater than 1 will give us positive. So 20 log of 10 means 20 dB, 20 log of 100 means 40 dB, 20 log of 1000 means 60 dB, and 20 log of 1 is 0 dB. So this is actually the baseline. So whenever I'm saying input is equal to output, that means ratio gain. So left side, whatever magnitude I am saying, magnitude gh j omega, this is actually the ratio gain, output minus input. Sorry, output divided by input. So whenever the output by input, that is gh is equal to 1, that is actually the baseline 0 dB in case of the simulograph paper. So in simulograph paper, log scale of frequency is used to accommodate a wide range of frequencies. So X scale is the log scale, log of omega. That's why it is called a semi-log. So Y-axis is very simple dB, linear range. X-axis is semi-log, or X-axis is actually logarithmic. So out of two axes, one axis is linear, another axis is logarithmic. So half of the axis is logarithmic. That's why it is called semi-log. What are the advantages of Bode plot? Very important question. So both low and high frequencies of transfer function can be shown or can be plotted in the graph. That means what are the amplitudes at very high frequency, what are the amplitudes at very low frequency. All these things can be plotted by using Bode plot. Gain margin and phase margin can be found with minimum computational effort. That means what is gain margin? Whenever the gain is crossing the zero mark, that means gain was greater than 0 dB. Now gain is now at 0 dB, and gain is going towards less than 0 dB. So wherever the gain is 0 dB, that frequency is called as gain crossover frequency. At that point, we find what is the system phase. Suppose if the phase is minus 140 at gain crossover frequency. So minus 40, minus 140 is actually 40 degree above the gain instability line. What is the gain instability line? Sorry, phase instability line. Minus 180. So again, I'll repeat, at gain crossover frequency, that means when the gain is going from positive dB to negative dB at a certain frequency, which is called as omega gc, at that time, the gain becomes equal to 0. At that point, at omega gc, find how much is phase. So suppose phase is minus 140, and how greater it is compared to minus 180. Minus 180 is called as a phase instability phase. So at omega gc, if we find that phase is 40 degree above than minus 180, that means phase margin is plus 40 degree. So positive phase margin is system is stable. Same thing we do in case of gain margin also we can find. So wherever the phase crosses minus 180 degree line and goes below, so exactly at which frequency the phase crosses minus 180 degree line, that is called as a phase crossover frequency. Phase crossover frequency is given as omega pc. Find what is gain at omega pc. Suppose at omega pc we find gain is minus 10 dB. That means still we can increase the gain by 10 dB till the system reaches the instability. So at omega pc, whatever system gain we find, if that is less than 0, so that amount, okay, so at omega pc we find that system gain is minus 10 dB. That means plus 10 dB is the gain margin. That means we can still increase the gain by 10 dB and still our system will be stable. So if both the gain margin and phase margin they are positive, system is going to be called as a stable system. So that's why it is said that in the second point that gain margin and phase margin can be found with minimum computational effort. So whenever you are drawing a Bode plot in the exam or anywhere, without asking, you have to find what is omega gc, what is omega pc. Now for every system, we might not find that the phase is crossing minus 180 and going down. Just now in the previous example I had given you, s plus 4 divided by s plus 3 into s plus 7, we found that the maximum negative phase can be minus 90. That means phase never crosses minus 180 and goes below. In that case, we'll be finding that gain margin will be infinitely positive. So not every case we will be finding that phase crossover frequency exists, but if it exists and if we find that at phase crossover gain margin is positive, then we can say that system is very much stable. Okay, so for stability condition, system should be having positive gain margin and positive phase margin. So system stability can be found out from Bode plot, and this goes without asking. So just if somebody asks you that draw Bode plot, with that you have to show how much is the gain margin and how much is the phase margin, and last line you have to comment on system stability. So the plots can be constructed with ease using asymptotic approximation, and Bode plot actually indicates a relative stability for a very clearly for any function. Okay, so these are the four advantages of a Bode plot. So first thing is both low and high frequencies can be accommodated. Gain margin, phase margin can be computed easily. They can be constructed with ease using asymptotic approximation. That means ease of drawing. And last thing is relative stability can be found out from Bode plot very clearly. So let us see one numerical, though I have not solved it by using semilograph paper. So later on I will show you some numerical with semilograph paper. But let us see this numerical, how to construct. And main pain point, I'll tell you, pain point is finding the resultant of all the amplitude plots that we have drawn. So you can see here it is given GSHS 160 by S plus 2 and S plus 20. So in this case, we have to actually find three Bode plots. One is for the constant at the numerator, which is not going to be 160. That is the first thing I am telling you, because this is not a transfer function form or time constant form. This is a transfer function, but this is not a time constant form. So first job in Bode plot. So now we are actually started solving some numerical officially. This is the first numerical we are solving officially. The complete numerical we will solve. So whatever is given is not a time constant form. What is a time constant form? It has to be 1 plus s by something. So here it is given as s plus 2. Okay, so in that case, it is not a time constant form. It should be 1 plus s by something. So how can we convert it into time constant form? First thing is take 2 common from the first factor and 20 common from the second factor. Numerator, nothing has to be done because there is no zero. There are only two pole system. If it is only two pole system, we will find that maximum phase of the system at omega tends to infinity can be minus 180, because this s plus 2, that means minus tan inverse omega by 2, s plus 20 minus tan inverse omega by 20. So both these things can give a minus 90-degree phase each as omega tends to infinity. So maximum phase we can find out in this case is minus 180. So after calculation, somebody, if it is find phase is crossing minus 180 and going below, means your calculation is wrong, because these two things, numerator 160 is always having phase 0. So what is the overall phase of this system? 0 minus tan inverse of omega by 2 minus tan inverse of omega by 20. So maximum phase for this system can be minus 180. But phase we will do later on. First see how to find the amplitude plot. So whenever this kind of thing is given, first thing, convert it into time constant form. So how to convert into time constant form? Just take 2 outside, 20 outside, so it becomes 1 plus s by 2 and 1 plus s by 20. Now here this 160 is getting divided with 20 and 2. So this becomes 4 divided by 1 plus s by 2 and 1 plus s by 20. Now converting any GSHS into time constant form is very necessary, and after that you will find the constant part is changing. Okay, so just looking at s plus 2 and s plus 20, you can find out that corner frequencies are 2 and 20. That is understandable. But this numerator constant, it was 160 and now it has become 4. Okay, so this changes. So students, those who are not following properly, just looking at it, they will do 160. That means 20 log of 160 they will do, and that is a mistake. Okay, so first convert the GSHS into time constant form, get s by something. Okay, s by something means 2 is a corner frequency and this is a pole. That means you will be finding that from 2 comma 0, a minus 20 dB per decade line is to be drawn. That will be the Bode plot of the first thing. From 20 comma 0, minus 20 dB per decade line has to be drawn. This is actually the Bode plot of 1 plus s by 20. And what is 4? 4 means actually it will be a line which will be parallel with respect to 0 line. And how much will be the height? It will be 20 log of 4. And 20 log of 4 we will find is equal to 12 dB. So it will be a parallel line with respect to 0 dB line, which will not be having any slope, which will be exactly parallel with respect to 0 dB line. So how many Bode plots we have to draw? We have to draw 3 plots First plot is actually we have to draw two Bode plots, one for magnitude and one for phase. But in magnitude also we have to draw three plots, and we have to add these three plots to find the resultant. What is the first plot? First plot is for constant, so it is 4. So first we have to see 20 log of 4. Okay, so plot for 4 is 20 log of 4, that is actually equal to 12 dB. Second plot is 1 plus j omega by 2. That means this is a slope of minus 20 dB per decade, because this is a single order pole, and single order pole is having a slope of minus 20 dB per decade. And this is also 1 plus j omega 20. This is also a single order pole, and this also will be having slope of minus 20 dB per decade. But this 1 plus j omega by 2 will start from the line 2 comma 0, start from the point 2 comma 0, and 1 plus j omega by 20, it will start from the point 20 comma 0. So let us see how many plots are there in magnitude plot. So three plots are there in magnitude plot. First plot is for 4, it is 20 log 4, this is 12 dB. Second plot is for 1 plus j omega by 2, this is slope of minus 20 dB per decade. So three amplitude plots are, one is for a constant 4, another is for corner frequency 2 radian per second, another is for corner frequency 20 radian per second. Now let us see how to draw it. So this is the first time I'm telling you this. So it is very easy to draw for the 12 dB thing. So just above 0 dB you calculate in semi-log paper what is the 12 dB, and just draw a line, and there you write down this is for 4. How to draw this line minus 20 dB per decade starting from the point 2 comma 0. Okay, so on the 0 dB line there is a point 2 comma 0, and then you have to plot. So this 2 will go to 20 and 0 will go to minus 20. So this is the first time I'm telling you how to draw slope from a point. Okay, so 1 plus j omega by 2. 1 plus j omega by 2 means that is actually having a corner frequency of 2 radian per second. Okay, that is what is shown here in the second thing. So how to draw it? So come to this starting point 2 comma 0, and there you have to draw minus 20 dB per decade. So decade of 2 is 20. Okay, so you have to first see on the semi-log graph paper where is the 20 frequency, and on that 20 frequency line you have to come below minus 20 thing. So every time 20 20 they are already getting too much of attention, so everything is 20. So that's why you should not get confused. Okay, so first point is 20, so 2 ka decade hai 20, and amplitude is falling from 0 to minus 20. So what will be the next point? Next point is this one. And what is this point? This point is 20, that is frequency is 20 comma minus 20 gain. So now you have to add this 2 comma 0 and 20 comma minus 20 line, and you can extend. So I have drawn it only up to 20 comma minus 20 point, but not necessary, you can extend it. Okay, so how to draw a line from a point with a given slope? Same thing will happen for this third part, that is 1 plus j omega by 20. So that means from the point 20 comma 0, so this is that point 20 comma 0, you have to first find what is that 20 comma 0 point, and there you have to draw a line with minus 20 dB per decade slope. So first you have to find out what is the decade frequency of 20. So decade frequency of 20 is 200. So on the similar graph paper you have to find first 20 comma 0 point, and you have to plot that, and then you have to go directly to decade frequency of that. So from 20 you have to go to 200, and it is falling by 20 dB. Okay, so whatever is this line minus 20 dB, in this is 20 comma minus 20, then towards right you will be finding 200 comma minus 20. So this is this point, so this is 200 comma minus 20 point. So now this 20 comma 0 and 200 comma minus 20, these two lines you have to join, and you have to extend it. So these are the three plots that you are plotting in this case. First plot is for 4 or 12 dB parallel plot. Second plot is minus 20 dB per decade line from corner frequency of 2, which is shown here, plot 2. And third plot is minus 20 dB per decade line, or falling slope from 20 radian per second, or 20 comma 0 point. So these three are the thing, and after that you have to add it. So that is a more difficult part, which is shown in the next page. So how to add it? Okay, so from so you have to see this thing separately, separate with respect to frequency. So how to draw it? So drawing is not at all difficult. Student find it difficult, but I'm telling you it is not at all difficult, because there are three frequency range. from point 1 or whatever up to 2. Okay, so up to 2 there is only 12 dB line. So if you see this resultant, so below is the resultant graph and top is the separate graph. So three separate graphs you can see here. So for 4 you are finding this 12 dB line. That is the first thing. 1 plus j omega by 2 you are finding this line. Okay, so 2 0 and 20 comma minus 20, and 1 plus j omega by 200 you are finding this line. Sorry, 1 plus j omega by 20, so this is 20 comma 0 and this is 200 comma minus 20. So these three now you have to add with respect to frequency. So initially from point 1 up to 2, only one amplitude is there, that is 12 dB. So that's why from point 1 to 2 you are finding that this line is coming. Okay, this line has come. That is up to point 1 up to 2 there is only one amplitude, that is equal to the 12 dB line. So you have come here, whatever is the point here. Okay, it doesn't matter, whatever is the point here. And then at this point you have to draw a minus 20 dB slope. So you can take this point and you are having a scroller kind of a thing. Okay, so that scroller kind of a thing. So already you have drawn this slope. So exactly the same slope you have to draw here, but up to which point? Up to 20. Okay, because from minus 20, so from 20 to 20, so this is a 20 point and there is a 20 point. So between 20 to 20 there are two amplitudes you can find. One is a constant slope. Constant parallel means it's having slope 0, and another is minus 20 dB per decade slope. So this constant line has come here, and after that the slopes are getting added. So top one is having slope of 0, bottom one is having slope of minus 20 dB per decade. That means from 2 up to 20, net slope or resultant slope will be 0 plus minus 20, that is equal to minus 20 dB per decade. So how can you draw it? You just have to draw the parallel line with respect to this. So what you are going to draw is resultant. So first come here, and then from here you just to have the draw parallel line to this, and you have to come up till point of 200. What's happening at 200? So we found here that whenever you're drawing this minus 20 dB per decade line, it is coming and touching it here. Okay, so this point you can very easily tell if you're drawing it by simulograph paper. From here, what's happening is at 20 radian per second, another slope of minus 20 dB per decade is getting added. So initial slope was 0. Between 2 to 20, the slope was 0 plus minus 20, that is equal to minus 20 dB per decade. And at 20 onwards, another slope of minus 20 dB per decade. So this slope is becoming minus 40 dB per decade. Okay, so how can you draw this line? So from here, you have to draw the next decade. So whatever is this line, 20. Okay, 20 to 200 you go, and then draw the slope of minus 40 dB per decade. So you can find here this is 0 slope, this is comparatively less slope, less drop, that is minus 20 dB per decade, and from here again you are falling very fast. This slope is called as minus 40 dB per decade. And here we write down, so this is 0 slope, between 2 and 20 this is minus 20 dB per decade, and between 20 and further means it goes up to infinity, the slope is minus 40 dB per decade. So this is the way we are supposed to draw the amplitude plot. Okay, and phase plot very easily you can find out, I told you. So the way you can find phase plot is tan inverse, okay, omega by 2 minus tan inverse omega by 2 minus tan inverse of omega by 20. So that you can find from here. So from this normal condition, normal GSHS also you can find out. So net phase, that is angle of j omega h j omega, that will be tan inverse omega by 2 minus, okay, negative of tan inverse omega by 2 minus of tan inverse omega by 20. And there you keep on substituting omega values. So start from like 0.1, so 0.1, 1, 2, 10, 50, 100 and 1000 and 10,000. Likewise some 7, 8 values you can plot, and maximum phase difference will be minus 180. So that you can find. I have not plotted phase for this thing, I have only shown the amplitude.